Hello class, today we are going to do chapter 7, Algebra Graphs, Functions, and Linear Systems. We'll be looking at chapter 7.2, Linear Functions and Their Graphs. Our objectives today are to use intercepts to graph a linear equation, calculate slope, use the slope and y-intercept to graph a line, graph horizontal and vertical lines, interpret slope as rate of change, and to use slope and y-intercept to model data. Now, we're going to graph using intercepts. All equations of the form ax plus by equals c are straight lines when graphed, as long as a and b are not both 0, and are called linear equations in two variables. We need to learn to locate the intercepts. To locate the x-intercept, we will set y equal to 0 and solve the equation for x. To locate the y-intercepts, we will do the opposite. We will set x equal to 0 and solve the equation for y. So let's graph 3x plus 2y equals 0. Solution. Find the x-intercept by letting y equals 0 and solving for x. So I'm going to take the function 3x plus 2y equals 6. I'm going to plug in 0 for this y. So I have 3x plus 2 times 0 equals 6. Well, 2 times 0 is 0. Boom, that's gone and out of the way. I'm left with 3x equals 6. I divide by 3 on both sides to get x by itself. I have x equals 2 is my solution here. So my x-intercept is 2, 0. Now let's find this y-intercept by letting x equal 0. So we're going to let this be 0 to find our y-intercept. Now we're going to solve for y. So we have 3 times 0. 3 times 0 is 0, so that cancels itself out. 2y equals 6. So now I just need to solve for y. I'm going to divide by 2. 6 divided by 2 is 3. So I have my y-intercept. Y equals 3. That'll be the point 0, 3. So the x-intercept is 2, so the line passes through the point 2, 0. So let's plot that here on the graph and see where that's at. 2, 0. I go right 2, and I plot this point here at 2, 0. That is my x-intercept. The y-intercept is 3, so the line passes through the point 0, 3. 0 up 3 is the y-intercept at 3. Now, all I have to do to graph this line, if I have 2 points I can graph a line, I can just draw the line between that y-intercept and that x-intercept. Very easily here. But if we want to verify our work by checking for x equals 1, we can plug x equals 1 into the linear equation. Now, you can go back and do that if you want to. Here's the equation. If you plug x equals 1 into this equation, you get 3 times 1 plus 2y equals 6. That means that 3 plus 2y equals 6, right? Which means if I subtract 3 and solve for y, I'm looking at 2y equals 3, which means that if I divide by 2, y equals 1.5, which means I have the point 1, 1.5. That's how they get this checkpoint of 1, 1.5, and what we notice is that point is indeed on the line, so we probably graphed the correct line. All we need is 2 points. The easiest way to get those 2 points most of the time is to find the y-intercept and x-intercept. Now, you also need to know what the slope of the line is. The slope of the line through distinct points x1, y1, and x2, y2 is the change in y over the change in x, sometimes called rise over run, which is y2 minus y1 over x2 minus x1. So we have this first point here, x1, y1. We have this second point here, x2, y2. All I do is I take this point y2, subtract y1, this point x2, subtract x1. Pretty simple, right? The rise is the y2 minus y1 part. The run is the x2 minus x1 part. Let's look at an example. Obviously here we don't want our x's to equal. We don't want x2 minus x1 to be 0. So we need to avoid the situation where they're the same thing. So we want to find the slope of the line passing through the pair of points -3, 1 and -2, 4. So we're going to let x1, y1 be -3, -1, and x2, y2 equal -2, 4. we obtain the slope such that the slope m equals change in y over change in x, or y2 minus y1 over x2 minus x1. Now, this is what we said. We said that the negative 3 is our x1, the negative 1 is our y1. We're saying that the x2 is negative 2 and the y2 is 4. So we put the 4 here minus negative 1. And then we put the negative 2 minus negative 3 on the bottom for our x's here. Now 4 minus negative 1, this minus a negative changes to a positive. 4 plus 1 is 5. 2 minus negative 3 is the same thing as negative 2 plus 3. That's where we get the 1. 5 over 1 reduces down to 5, and therefore 5 is our slope. The slope of the line is 5. Now, if you have the graph here, like we do on this right-hand side, and you didn't want to use this technical definition here with this equation, what you could do is you could start at this point, negative 3, 1. You could count up to see what the rise is. 1, 2, 3, 4, 5. I have to rise 5 points to get on plane with this other point. And then I have to count 1 over to get there. So this tells us our rise is 5 units. Our run is 1 unit, the same thing that we got here before we simplified to the last step. Therefore, 5 over 1 is 5. So we could technically find the slope from the graph picture or from the points from the graph. Now that we know how to find the slope, let's look at the slope-intercept form of the equation of a line. The slope-intercept form of the equation of a non-vertical line with slope m and y-intercept b is y equals mx plus b. M is your slope, b is your y-intercept. So if I have the equation y equals 2x minus 4, the slope is 2, the y-intercept is negative 4. If I have the equation f of x equals 1/2 x plus 2, the slope is 1/2, the y-intercept is 2. The number in front of the x is your slope, the constant is your y-intercept. So let's look at graphing this. The slope-intercept form of an equation of a line continued looking at graphing. Y equals mx plus b using the slope and the y-intercept. Step 1, we will plot the point containing the y-intercept on the y-axis. This is the point 0b because the b is the y-intercept. Step 2, we want to obtain the second point using the slope m. We write m as a fraction using the rise over run technique, starting at the point containing the y-intercept to plot the point. We use a straight edge to draw a line through the 2 points, and we draw arrowheads on the end of the line to show the line continues indefinitely in both directions. So let's graph the function y equals 2 over 3x plus 2 by using the slope and y-intercept. Since the graph is given in slope-intercept form, we can easily find the slope and the y-intercept. The slope is the number in front of the x, the 2/3. The y-intercept is the constant, which is 2. Now the slope, I just want to reiterate something here. The slope is the number in front of the x. The slope does not include x. So the slope is 2/3, not 2/3 x. The slope is just the 2/3. It doesn't have an x on it. It's just the number in front of the x is what the slope is, and then the y-intercept is the constant there on the end. So step 1, we want to plot the point containing the y-intercept on the y-axis. This case, we found the y-intercept to be 0, 2. So we go 0 on our x-axis up to 2. We have plotted this point right here for our y-intercept. Now we want to obtain the second point by using the slope m. The slope is already given as a fraction, so I'm just going to use it as is, 2/3, which means we rise 2, so I go up 2 points, 1, 2, and then I go over 3 points. I run 3 points, 1, 2, 3. And now I have a second point here that I can plot. Okay, so I plotted my y-intercept. I've used my slope to find a second point. You can use your slope to find a third point, fourth point, but you really only need 2 to plot a straight line. We plot this second point. We use a straight edge to connect the 2 dots. We throw arrows on the end, and hey, our line is graphed. Let's graph the linear function 2x plus 5y using the slope and y-intercept. Now, originally, when we started this lecture, we used our x-intercept and y-intercept to graph an equation that was put in this standard form. But here we want to use the slope-intercept method. In order to do that, it needs to be in slope-intercept form. So what we have to do is solve for our y variable here. In order to do that, we got to get y by itself. Once we solve and get y by itself, then we'll have it in slope-intercept form, and we can use the slope and the intercept from that equation, that simplified slope-intercept equation, to plot our point. So the first thing we want to do is get y by itself is subtract 2x from both sides. It's essentially what we're doing here, so that the 2x's cancel out, and I'm left with 5y equals negative 2x. Now, I need to get y by itself, so I'm going to divide by 5, like I did over here. So I divided by 5, divided by 5. These 5's cancel out. I'm left with y equals negative 2 over 5x. Now, we don't have a technical number written over here, so our y-intercept is assumed to be a 0. So this is our slope-intercept form, where essentially our y-intercept is 0. So our slope from this slope-intercept form circled in red is negative 2/5, and our y-intercept is 0. Or if you write it as a coordinate point, it would be 0, 0. So let's graph these. We'll start at the y-intercept 0, 0. That is our point that we start plotting right here, plotted in black. Then we're going to use our slope here to find another point. So our slope is negative 2/5. So I'm going to apply the negative to the 2 part and count down 2, 1, 2, and right 5. 1, 2, 3, 4, 5. Boom, I have a point here. At 5, negative 2 now, I have my 2 points. I use a straight edge to connect them and draw my line, throwing my arrows on the end. Very simple. Let's graph a horizontal line. So what happens if I have something like y equals negative 4 in the rectangular coordinate system? All ordered pairs have y coordinates that are negative 4. That is essentially what the equation y equals negative 4 is telling us. We don't have to have an x in it. This is just telling us that all values are y equals negative 4. So any value can be used for x. We can graph 3 ordered pairs in the table. Negative 2, 0, and 3. And all of those are going to have y value negative 4 because y is always negative 4 in this equation. It says it right there. Y is always negative 4. Y equals negative 4. There's no change. It's always negative 4. It doesn't matter what x you choose. Even if you choose 1 billion, 1 trillion, negative 2,000. It is still y equals negative 4 for all points. So, essentially, we can go to any x that we want to. We can go to negative 2, and the y point is still going to be negative 4. We can go to 0. The y point is still going to be negative 4. We could go to 3. Y point is still going to be negative 4. So what we wind up with is a horizontal line through y equals negative 4. If we have horizontal lines, we can have vertical lines. A horizontal line was where y equaled. A vertical line is where x equals a constant. So it says graph x equals 2 in the rectangular coordinate system. All ordered pairs have the x coordinate of 2. Any value can be used for y. So we can graph the ordered pairs 2, negative 2, 2, 0, 2, 3, and draw a line that passes through all 3 points. That's going to give us a vertical line. So what we can see for the graph of x equals 2, that means when I go to x equals 2, all these values of y are still going to result in an x value of 2. Doesn't matter what the y is, the x is always going to be this value of 2. So we wind up with a vertical line on x equals 2. Now, something to note here is that no vertical line represents a linear function, because a vertical line fails the vertical line test itself. All other graphs of lines are functions, except for vertical lines. So you can draw any other line you want to, any other straight line you want to here, and it will be an actual function. But if you draw a vertical line is not a function. Horizontal line's a function, vertical line, not a function. Diagonal line, whether increasing or decreasing, is a function, but a vertical line is not a function. So, let's define it. Horizontal and vertical lines. The graph of y equals b, or f of x equals b, is a horizontal line, and the y-intercept is b. So, this horizontal line is just a line that goes through that y-intercept b. The graph of x equals a is a vertical line. The x-intercept is a. And you have that vertical line through that x-intercept point there, a0. Now let's define slope as rate of change. Slope is defined as a ratio of a change in y to a corresponding change in x. Slope can be interpreted as rate of change in an applied situation. So let's look at an applied situation. In 2016, college freshmen were more politically polarized than they had been in the last 36 years. The line graphs in the next slide show the percentage of college freshmen who were liberal or conservative in 1980 and in 2016. Find the slope of the line segment representing liberal college freshmen. Round to 1 decimal point and describe what the slope represents. So let's look at the slide here. So we can see here for liberal in 1980, 21% of college students had that political orientation in 1980. In 2016, 36% of college students had the liberal political orientation. And essentially what we want to do is we want to find this slope or rate of change from 1980 here to 2016. Easy enough, right? So all we have to do is let x represent a year and y the percentage of liberal college freshmen for that year. The 2 points on the line segment for liberal college freshmen have the following coordinates: 1980 and 21, and 2016 and 36. We can clearly see that from the graph. It has it labeled for us where we circled them. So our slope here is our change in y over our change in x. Well, our x1 would be, x1 would be 1980. Oops. Our y1 would be 21. Our x2 would be 2016. Our y2 would be 36. So we're going to do y2 minus y1, 36 minus 21. x2, 2016, minus x1, 1980, gives us 15 over 36, which is approximately 0.4. So the slope indicates that from 1980 through 2016, the percentage of college or liberal college freshmen increased each year by approximately 0.4. The rate of change was approximately 0.4% per year. Simple enough. So let's look at modeling data with slope-intercept form of the equation of the line. Linear functions are useful for modeling data that fall on or near a line. So technically what we could do is we could model this data, which is essentially what they've done in example 7, with this slope given that y-intercept. So if we wanted to model this, we now have the slope. So we would have y equals mx plus b. We're just going to model the liberal one that we solved for. We have the slope 0.4x. And what we would need is the y-intercept, which we could solve for. Now here we have 1980, 21. What you have to be careful of here, and what is done in Math 108, if you care to go to Math 108, is our 0 point here is 1980. So in Math 108, we do what's called an alignment. And if you were to align this, where 1980 was year 0, and 1985 was year 5, it would be very simple to see that your y-intercept here, where it hits at your y-axis, would be the 21%. So you could write your 21 there. Otherwise, what you would have to do, if you did not align it, and you wanted to use the full year, is you would have to solve for that b point. So you would have to do y equals 0.4x plus b, and then you would have to plug the point in. So what we would do is we would plug 21 in for our y. We would plug 1980 in for our x, and then we would solve for our b value. And whatever our b value that we found here, we would use to plug back into our original equation here for this b, and then we would have the equation of our line here that modeled the liberal political orientation of U.S. college freshmen. So, linear functions are very useful for modeling data, especially when they are that straight or nearly straight line. This concludes chapter 7.2. If you have any questions, please reach out to me via email. I'll get back as soon as I possibly can. Please proceed to try the homework with this particular section. Let me know if you have any trouble whatsoever. This is going to be one of the last sections we do in chapter 7. So please make sure you've got it down. Graphing is very, very important. Thank y'all, and see you next time.